Dr. Rao, there is no audio from your side.
Yes.
There is no audio from your side. Please check.
Just now it is audible, sir.
Yeah, now it is audible.
Oh. Now it is audible, sir.
Yes, sir, you are audible.
Okay, sir. So next topic is about the metamaterials. Next is about the recent advances in radio frequency energy harvesting. And the next is about the recent advances in radio frequency energy harvesting using the hydroelectric and permittivity. Next, I'll wind up my presentation with conclusion. First is introduction, like the wireless power transfer system. It portrays a unit, okay, which that emits electrical power from one place and captures it at another place. Where there is no connection between the transmitter and the receiver. Okay, generally the wireless power transfer was conceptualized nearly a century ago. It is now being used in various areas of research. Okay, this energy transmission that goes in a cordless way, it can change a traditional usage of the energy in diverse applications such as implantable devices, mobile electronics, aerial vehicles, electric vehicles, and so forth. Generally, this wireless power transfer, it denotes the transmission of electromagnetic energy from a power source to a load, where without the conductor connection, but this is not a new concept. Okay, it was used in the way back in the 1860s. Okay, but however, there was the absence of a logical theory that is attributed these phenomena ambiguously to electromagnetic induction. Okay, the voice is audible, sir.
Yes, sir, audible, very much audible, sir.
Okay, thank you. Okay, it was in the past decades, these several researchers have observed the transmission of electrical energy without wires. However, there was an absence of logical theory that attributed these phenomena ambiguously to electromagnetic induction. Okay, the beginning of the concise explanation of this wireless power transfer dates back to 1860s, when the scientist James Clerk Maxwell demonstrated Maxwell's equations, okay, establishing a theory that combined the electricity and magnetism to electromagnetism, predicting the existence of electromagnetic waves. Later in the year 1891, there was a remarkable development in wireless power transfer technology that was demonstrated by the scientist Tesla. Okay, the scientist Tesla, he experimented with transmitting power in by inductive and capacitive coupling using spark excited radio frequency resonant transformers, now called Tesla coils. Okay, it was also used in the year 1963 by the scientist Brown, where he exhibited a microwave power transfer system realizing long distance wireless energy transfer at the city called Rayathan. Now coming to what is this energy harvesting. Now, with the increase in the advancement and progress in the field of wireless power transfer, okay, the energy harvesting phenomena has become a very sought after area of research. The energy harvesting has become a recurrent topic of research during the last few years. Energy harvesting or energy scavenging is nothing but a process where the renewable energy sources are converted into electrical energy. Okay, the electrical energy that is converted can be stored in small wireless devices like batteries. Now, why there is a necessity to go for the energy harvesting is by the year 2060, many countries in the world will be exhausted with fossil fuels and trying to implement sustainable and greener technologies. Okay, as non-renewable energy sources do not last long enough in nature, hence we have to go or depend on renewable energy sources like electromagnetic energy or the thermal energy, wind energy, solar energy, etc., which are utilized to make the energy harvesting process more efficient.
Sir, your slide is not changing.
Okay, sir. Now changing, sir.
Sliding is not changing, sir. Please change.
So I think you have to select the full screen mode, that entire screen
Yeah.
sharing. I think you have shared only the window of your this PPT, but while
Okay.
selecting for sharing, you select the entire window, entire screen. Then I think we can see. For you it is moving, but for us it is not moving.
Okay.
You have selected only the Microsoft PPT.
Okay. Sir, I'll send the PPT to your email, sir. Can you share from your side? Sir, I'll send the PPT to your email, sir. Can you share it from your side? Hello, sir.
Yeah.
Sir, can I send the PPT to your email so that you can share it from your side, sir?
Sir, actually, you will mail me the PPT and what I will share the PPT.
Yes, sir.
Sir, actually, is it not possible from your side?
It is not moving, sir. For me it is moving, but I don't know, sir.
Sir, actually, just I am directing you. You just yeah, open your slide.
Yes, sir.
You share your slide.
Just a minute.
You share your slide.
Yes, sir.
You share your screen.
Share the entire screen.
Yeah, you share the entire screen.
But
as earlier you have shared, you kindly reshare your entire screen, please.
unable to share the screen, sir. That entire screen.
So you try again, please.
Unable to share the entire screen, sir.
Sir, what problem is showing in the screen?
It is not showing the option share, sir. That. Just a minute.
Sir, you do one thing that you send me a PPT in an email. Let me try.
I'll just try once, sir.
Okay. Sir, you mail me your PPT.
Yes, sir.
You mail me at onirman2025 @gmail.com.
Yes, sir. This the email from which you are communicating.
Yeah. Please send.
Okay. I sent it, sir.
Let me check. I have received your PPT. Let me open it.
Okay.
So now it is visible.
Yes, sir. Now it is visible.
Okay, sir. Please go ahead.
Okay. Please go to this. Sir, please go to slide number 6. Sir.
Okay. Then,
Slide number 6. Sir.
sir, please, actually slide number is not mentioned.
Just like
You tell me the slide in which I should stop. Okay.
okay, sir. Go to energy harvesting.
Yeah. Okay, sir. Please go ahead.
Okay, sir. But here the slides are not changing, sir.
Slides are not changing.
Go to next slide. Now it this you can stop here.
Okay, sir. Please go ahead.
Okay. Now by the year 2060, many countries in the world will be exhausted with the fossil fuels and trying to implement sustainable and greener technologies. As non-renewable energy sources do not last long enough in nature, we have to depend on renewable energy sources, that is electromagnetic energy, thermal energy, wind energy, solar energy, etc., which are utilized to make the energy harvesting process more efficient. So next slide, sir. Okay, sir. So this is the general block diagram of radio frequency energy harvesting, where the transmitting antenna, generates electromagnetic waves in free space, which are these EM waves are collected by the receiving antennas. At the receiving side, we have three major blocks. That is, first is the impedance matching network. Impedance matching network is a block which tries to match the impedance of the receiving antenna with that of the output. Next, we have the rectifier or the voltage multiplier. Rectifier is defined as a device which converts the AC signals into DC signals. We generally use the Schottky diode for the gigahertz frequencies. Next, they have the voltage multiplier, where the voltage or the signal is getting amplified. So next slide.
Sir, actually the thing is that as an administrator, I need to take many things from my side. That I need to take screenshots, I need to take attendance, and whatever it is. Yes. So whatever you sir try to finish as soon as possible, because I need to do all the formalities.
Yes, sir. Okay.
Okay. Yeah.
Okay. Now the next one is what is called as a motivation for the radio frequency energy harvesting. The concept of energy harvesting or energy scavenging is defined as a technique for reaping the energy from the external environment using different methods like the vibration excitation, solar energy conversion, and pressure gradients. The radio frequency energy harvesting, it promises a tremendous scope for the replacement of small batteries in low power electrical devices and systems. Okay, now these replacing batteries holds vast potential for replacing batteries or increasing their lifespans. Currently, many batteries power a majority of low power remote sensor devices and various embedded equipment. And additionally, the batteries have the finite lifetime and they require periodic replacements. Okay, and next. Sir, next slide. Okay, additionally, other motivation for the radio frequency energy harvesting is the processing of battery waste is a critical problem. A majority of these batteries, they end up in landfills, leading to the pollution of the land and water underneath. The most effective solution to reduce this battery waste is to just avoid them. So here in this table, you can see the various sources of energy harvesting like the solar, vibration, thermal, and RF. The source for the solar is the photovoltaic, and for the vibration it is the piezoelectric, electrostatic, and electromagnetic. And for the RF source, it is the antenna. Now the advantages of the RF energy harvesting over the other harvesting techniques is it is always available and implantable. So next slide. Now, these are the various radio frequency energy harvesting evaluation metrics. The first parameter is what is called as your operation range. The operation range is defined as mostly related to this operation frequency. Generally, the transmission at the higher frequencies is attenuated by the atmospheric conditions more than at the lower frequencies. Therefore, it is if the application of the wireless power transfer is for implantable devices, then the transmission frequency could not exceed the megahertz range. So the next most important parameter of a radio frequency energy harvesting or the evaluation metric is the RF to DC power conversion efficiency. That is a ratio of P load upon P received. That means how much amount of the received AC power is converted into the DC power. So next slide. So third parameter is what is called as your resonator quality factor. The quality factor is generally a dimensionless parameter or value that describes how strong the resonance is and the bandwidth of resonance. It is defined by the equation Q is equal to 2 pi into energy stored upon energy dissipated per cycle. The fourth evaluation metric or the parameter is the sensitivity. The sensitivity of a RF harvesting system or the WPH system is defined as it is the minimum limit of incident power that is required to trigger the operation of the system. So the next slide. Okay, now coming to what are called as the metamaterials. Metamaterials, the word meta in the word metamaterials is derived from the Greek word, which is meaning beyond. Metamaterials, they are defined as the artificial or man-made materials, engineering materials that exhibit uncommon and exotic properties that are not readily available in the nature, which is going beyond limitations encountered when using traditional materials in the micro and optical applications. The metamaterials was first theoretically investigated by the scientist Vesilago in the year 1968, who introduced the electrodynamics of substances by simultaneously getting the negative values of electric permittivity and magnetic permeability, which are the properties of your metamaterials. So next slide. So this is a general categorization of metamaterials based on the permittivity and permeability values. If you can see in the first quadrant where both permittivity and permeability are positive, which leads to forward propagation of electromagnetic waves. Next, if we go for the second quadrant where epsilon is negative and permeability is positive, and the fourth quadrant where the epsilon is positive and mu is negative, when either of the two parameters is negative, there is no propagation of EM waves. And next, if we go for the third quadrant, that is here where the epsilon and permeability is negative, we call it what are called as your metamaterials. The negative values of permeability and permeability lead to the negative value of the refractive index of the EM wave that is passing to the. So next slide. The next slide. Now coming to these recent advances in radio frequency energy harvesting using metamaterials, one of the most prominent applications of metamaterials is the energy harvesting. Researchers are finding metamaterials as very prominent and good candidates in the field of energy harvesting to extract maximum energy from the non-renewable energy sources and convert into DC power. Okay, recently researchers have reported that these metamaterials can be utilized for improving the transfer efficiency of the near field and far field RF energy harvesting applications, particularly in the area of near field RF energy harvesting systems. When the metamaterial slab is placed between the transmitter and receiver coils, the magnetic field lines can be focused due to the negative refractive property of the metamaterial slab, and coupling between the transmitter and receiver coils can be enhanced due to the evanescent wave amplification property of the metamaterial slab. Okay, consequently, this leads to the improvement of transfer efficiency of the RF energy harvesting system. So the next slide. Okay. Yes. So this is the general classification of metamaterials that are based on RF energy harvesting. This can be classified according to two things. First is the dimension of the slab. Other is the position of the slab. The dimension of the slab can be one-dimensional, two-dimensional, or three-dimensional. And the position of the slab can be in between the transmitting and receiver systems, or the transmitting and receiver coils. The second position can be where the metamaterial can be placed in front of the transmitting and receiver coils. The third scenario is where the metamaterial slabs can be placed at the back of the transmitting and receiver coils. And the fourth scenario is where they can be placed at the side of the transmitting and receiving coils. Okay, next slide, sir. You can go to next slide. Okay, now if you observe here, okay, this is the conceptual principle of two coil based metamaterial RF energy harvesting. Okay, in the figure A, figure 5A, between the transmitting and receiving antennas, there is no metamaterial slab. So most of the the EM waves that are transmitted from the transmitting to the towards the receiving coil are not absorbed by the receiving coil. But after I place the metamaterial slab in between the transmitting and receiving coils, okay, most of the EM waves are absorbed by the receiving coil. So next slide. Yes. So that is how you can improve the wireless power harvesting or the radio frequency energy harvesting. This second other research that is recent advances in the radio frequency energy harvesting using metamaterials is that depicts that metamaterials can mitigate the RF to DC conversion efficiency that is caused by the misalignment owing to the metamaterial evanescent wave amplification property. Okay. So what is the next research that is happening is whenever there is a misalignment between the transmitting and receiving coils, that means there can be a misalignment in the lateral direction as well as the angular direction. Okay, so what is happening here is whenever there is a misalignment in terms of lateral direction and angular direction of the transmitting and receiver coils, the metamaterial, it amplifies the evanescent waves, leading to the increasing in the magnetic coupling between the transmitting and receiver coils for both the lateral and angular misalignment conditions. So generally the experiment results show that the metamaterial slab can improve the RF to DC efficiency of this RF energy harvesting, and it can compensate the impacts of the misalignments on the system. So generally, whenever there is a misalignment also, the metamaterial slab improves the RF to DC efficiency from 25.3% to 57.9% in an aligned condition. Under the lateral misalignment condition, Okay, the RF to DC efficiency of the system with metamaterial shows that there is an improvement by 33.1% at 10 centimeters and 40 centimeters. Sir, can you please go to the previous slide, sir? So this is what is the, one of the latest research that is happening in the RF energy harvesting using metamaterials. Now you can see that the transmitting and receiving coils are misaligned there. They are not in the same line. That means there is a lateral misalignment. In the second one, there is an angular misalignment. That means the receiving coil is not at the same angle as your transmitting coil. So even if there is a misalignment in terms of lateral as well as angular, by inserting the metamaterial slab between the transmitting and receiver coils, you can still improve the RF to DC conversion efficiency or the wireless power transfer efficiency. So next slide. So these are the various types of metamaterials that have been used to improve the RF to DC efficiency and even the wireless power transfer efficiency. The second column shows the configuration of the metamaterials and the number of slabs that have been used. The various kinds of metamaterials that have been used are like, square spiral resonator consisting of 2 slabs, the square spiral resonator consisting of 1 slab. Okay, the square spiral resonator single-sided, double-sided consisting of 1 slab. Okay, other metamaterial is your hexagonal spiral resonator of double-sided 1 slab. So like this, the RF to DC efficiency and the wireless power transfer efficiency has been increased. Okay, in the last column, it has been mentioned something by something. So a numerator is indicating what is after inserting the metamaterial, and the denominator is indicating before inserting the metamaterial. So the next slide. Okay, these are the various configurations of your metamaterial. Okay, consisting of one-dimensional. And next slide shows some of the configurations for your two-dimensional. The next slide. Okay. Please go to the next slide.
Sir, am I audible?
Oh, audible, sir.
Yes, sir, please go ahead.
Please go to the next slide, sir. Sir, can you please go to the next slide? Yes, sir. So this is the yes, sir, previous slides. Yes, this is the other. Yes, sir. This is other recent advances in radio frequency energy harvesting using metamaterials. This is where the metamaterial is using either the high dielectric or high permittivity material. Sir, can you go to next slide? Previous. Yes, sir. Here you can see the transmitter coil and the receiver coil. Okay, here the metamaterial is made of 2 types here. First one, it is made of high dielectric, and the other one is it is made of high permittivity. Okay. Sir, next slide, sir. Okay, so here subsequently the researchers have proposed the RF energy harvesting system based on high permittivity metamaterial instead of the high dielectric metamaterial. Okay, the RF to DC conversion efficiency is 9.1%, whereas that using the high dielectric it is approximately 30%. The next slide, sir. Okay. So to conclude my talk, there has been a review of recent progress and effects of metamaterials on the RF energy harvesting. It has been discussed, and the brief history and fundamentals of metamaterials have also been reviewed. Some of the current state of art methods to enhance the RF energy harvesting efficiency have been highlighted, including the improvement of RF to DC conversion, compensation for misalignment conditions, and usage of high dielectric and permittivity metamaterials. And finally, various metamaterials have been compared in terms of performances, in terms of energy efficiency, like one-dimensional, two-dimensional, and three-dimensional, and also the position of this slab. The next slide. This is last. Thank you. So this
Sir,
is the
there
end
is
of.
no further slides. There is no slide further, sir. It is the
Yes,
last
sir.
one.
This is the last slide. Yes.
Okay. So now I will ask participants to raise their queries if you have any.
Yes. Sir.
Participants, now ask your queries.
Sir, I have
Hello,
one
sir.
query.
Okay,
Yes,
go
sir.
ahead.
Yeah.
Go ahead.
Sir, while designing the rectifier for RF energy harvesting, how can I
Yes, sir.
increase the power conversion efficiency of the rectifier?
How can you increase the power conversion efficiency?
That is, sir, RF to DC conversion efficiency.
Yeah. Generally, they use the Schottky diode, madam, to convert that RF to DC efficiency. But even I do not know why they generally use the Schottky diode only, because recently I organized an DML lecture, madam, on the wireless power harvesting in our college through IEEE MTTS. There also I asked the same question to the speaker. A speaker told she'll be getting back in 2 weeks. Like so, because even I do not know exactly what is that. Why they use only Schottky diode?
Okay, sir.
Okay,
Thank you,
okay,
sir.
sir. Thank you.
So, is any other participants with any kind of questions?
Excuse me, sir.
Yeah.
I have a query, sir. How the different type of losses, that means power loss, conductor loss, dielectric loss. So these type of losses can be handled in metamaterial. Would you please highlight on this factor? Hello, sir. Have you got my question?
Yes, sir. Can you please repeat it, sir?
How different type of losses while designing some energy harvesting system by metamaterials, how the different type of losses like
Yes, sir.
dielectric loss, conductor loss, power loss, so this type of losses how we can handle in metamaterials?
Yes, sir. That one thing is you can use the one technique that I've discussed, sir. Like, you can place the metamaterials, at the front of the transmitting and receiving coils. Other one behind the coils and inside of the coils. I know that the conductor losses that you are asking, they can handle with that, but how well they can be handled, I have not still gone through in detail. But one thing
Okay,
is sure
sir.
that those conductor losses, power losses, they can be handled by positioning the metamaterial slab like in front, back, or sideways like that. But how will they contribute to which parameter, like power loss or conductor loss? That I have not completely studied.
Okay, thank you, sir. Thank you.
Okay.
Sir, cannot be metamaterial used for making the coil?
Hello.
Hello, sir.
Yeah, please audible. You are audible. Go ahead.
Sir, metamaterial cannot be used for making the coil itself instead of placing the slab.
Metamaterial?
Sir, we can make coil also using metamaterial, the conductors, or only we can use the dielectric slabs.
Coils can be used for conductors also, sir.
Okay, sir.
Hello, sir.
Hello, sir.
I want to ask normally what is the radiation pattern of the metamaterial based antenna? I mean, which direction it is desirable?
Like it depends upon the application, sir. Like let's say you want a directional antenna.
Okay.
Uh,
But don't we
like-
think that if it is energy harvesting, then the
Yes, sir.
antenna should be capable of collecting energy from all the direction?
Yes, sir.
Because if we use metamaterial, then in most of
Yes.
the cases,
Huh.
the radiation pattern will be directional only, as far as I
Yes.
know.
Yes.
Yeah. So is there any way to make it omnidirectional so that we can collect energy from all the direction?
I have no idea, sir.
Oh, okay,
Yeah.
sir. Thank you, sir.
Okay, so any other participants, do you have any questions?
Sir,
Yeah.
Sir. Sir.
sir, while using antenna and rectification process, the impedance matching will occur, mismatch will occur. How it will rectify?
When impedance mismatch is there?
Yes, sir. While combining antenna and rectification, impedance
Yeah.
mismatch will definitely occur, sir.
Yeah.
How I
Yes, sir.
can rectify this process?
You can remove the mismatch by using the different matching networks, so like T matching network, pi matching network, those things.
Yes, sir.
So any other participants with any kind of questions?
Sir, I have one question.
Yes, madam.
Sir, while designing the rectifier, how to increase the output voltage of the rectifier? Like, what component should we choose to increase the output voltage?
Yeah. Actually, Ms. Pooja Das, I would like to tell you, his presentation is related to metamaterial. Actually, the question you have asked that is totally related to the rectifier part. That may not be answerable over here, I think. So
Okay, sir.
actually, this question you can ask the question to other speakers who will be talk mostly on the rectifier part. Okay. Okay.
Hello, Rao sir.
Yeah.
Yes.
Sir, thank you very much for the wonderful information about metamaterials and RF energy harvesting. It's a very new topic for me.
Yes,
Sir, your
Actually,
slides are very correct.
no, actually, this is my first talk on only second talk on metamaterials based RF energy harvesting. Sir. Actually, first talk I had given in my college. There I was little fearful. Here also I'm little bit fearful, but little better, sir. That's the thing.
Sir,
Okay.
your presentation is quite connective. It's simple and very much to the point.
Yes.
And you have kept it precise also. So, sir, I have a
Hi.
request, sir. If
Hi.
you allow, can you just share the PPT with all participants?
Yes, sir. I will send it to Anirban Karmakar.
Yes, sir. Kindly, sir.
Sir will share it to all participants.
Yes, sir. Kindly, sir. Thank you so much, sir. What a wonderful session.
Thank you, sir. Thank you.